let's begin with the second session. Thanks, Dylan, for speaking again, and take it on.
Wait, am I good to go?
Yeah. Please go ahead.
Oh, okay, awesome. Cool, yeah. I mean, thanks again. Thanks for coming back to part two. Yeah, so we're gonna sort of kick off where we left with part one. So if you remember from the first part of the tutorial, we talked about these three challenges, exploration, credit assignment, generalization. We saw how to solve them on their own. We saw how to solve them in pairs. And now in this part, we want to try to solve them all at the same time. Like, in other words, how do we explore in systems where we have a long horizon and do this while generalizing across states? Okay. I want to briefly remind why we care about this generalization issue. And the point here is we want to be able to do RL in sort of high dimensional continuous state spaces. So, you can think of a setting where like states are images from a camera. So, the state space is intractably large on its own, but like just in supervised learning, we want to be able to use modeling and pick some sort of hypothesis class that will allow us to generalize across states and maybe even actions. Now, like, okay, if you think back to the first part of the tutorial, like for example, in the contextual bandit problem, there we were mostly using modeling to, or like using our hypothesis class script F to capture things like rewards. But when we come to the full RL setting, there are a few different ways that we can approach modeling and function approximation. And I'm going to go over these sort of ordered by how strong the modeling assumption is. So one approach, which we actually already saw like implicitly in some sense when we worked with policy gradient methods in the first part, is pick a restricted class of policies pi. So for example, like policies that are parameterized by neural nets. Like here, big pi would be our hypothesis class. Another approach is that we can use what are called like value-based methods. And here we're using a restricted class of hypotheses script Q, which is trying to model the value functions in the MDP. And this could mean we want our class to be able to capture all possible value functions, or it could maybe mean we're just trying to capture the optimal value functions. And lastly, and I apologize if there's confusion with the terminology here, is what are called model-based methods in the literature. And the reason I say that is just because all of these approaches involve modeling in some sense, but these are the ones that people call model-based explicitly, right? And this means our hypothesis class is like some subset of MDPs. So we're directly parameterizing transition probabilities and rewards. So like with all of these approaches, we like algorithms that can handle general classes of hypotheses, be it like linear models or neural nets. So now that we have our hypothesis class, value functions, probabilities, I'll briefly restate the statistical goal for this setting. We're going to follow the same episodic RL setup as in the first part of the talk, so I won't focus on this. The important point here will be that our goal will be achieve either sample complexity or regret that's polynomial in like the horizon and the target accuracy, but most importantly in the statistical capacity of our function class script F. And in doing this, we're going to typically make some assumption along the lines of realizability that says, well, the hypothesis class we're working with is indeed powerful enough to like represent, say, Q functions or transition probabilities. And I mentioned statistical capacity here. When I say statistical capacity, I'm thinking back to these complexity measures we saw in part one, like VC dimension and Rademacher complexity. So like for concreteness, you can think of like comp script F. This is the capacity. This could be like log cardinality of the function class or finite classes, or it could be like the feature dimension D if we're doing linear models. But the point is, this is not explicitly going to depend on the number of states, which will reflect the fact that we are generalizing.
Sorry, Dylan.
Oh, yeah.
One question about the previous slide. Maybe I should have asked in the first part.
Sure.
So here you're assuming that you can always restart the system from some arbitrary distribution of states at every period?
Oh, I'm assuming that this initial state distribution is fixed and is unknown to us.
Okay, but would it be possible that there are many systems where once you've alter them, you can't go back. Like, like once you've say run on one episode, you
Yeah.
have to sort of like restart maybe from a different distribution because you affected it. Is that something that's not captured by this setting?
That's not captured by this setting. I guess I can say more about that maybe at the end of the tutorial. Some of the things we'll discuss are actually pretty easy to extend to that setup. Others, not so much. I mean, it depends on this. It depends on the exact style of guarantee you're going for.
Okay.
Yeah.
Thanks.
Cool. Okay. Yeah. So to motivate some of the approaches we're going to look at here, I want to kind of explain why achieving these statistical learning style sample complexity guarantees in the general RL setting is difficult. And this really comes down to an issue called distribution shift. Okay. So the idea behind this issue is kind of easiest to explain if we think about what an idealized reinforcement learning algorithm might look like. And I've written an example out here. So let's just go through this step by step. So our idealized RL algorithm, let's say we have some policy we've computed. We're going to run it and we're going to gather some data from the distribution script D that it induces over, like states and actions. Using this data we've gathered, we're going to fit some hypothesis class or fit a hypothesis, which could be like value functions or transition probabilities using the data set we've collected. Then we're going to somehow update the policy using this hypothesis, right? This could be like taking the greedy policy if we estimate Q functions. We're going to keep doing this. And the hope would be that our performance will improve as we do this over time. Like we get better at estimating things. But okay, what's the issue here? I mean, the issue is that like if we think of supervised statistical learning, or if we think about like generalization, this is something that tells us when we fit this hypothesis class or fit this hypothesis F hat, this is going to do a good job at predicting on, future data if we gather it from the same distribution script D that we used to collect our data set. But the problem is like, even though F hat might be a good fit on this distribution script D, we're going to update the policy to pi t plus 1, and we might be completely useless at guiding this policy once we update it. Because for example, pi t plus 1, it could take a different action from pi t just at the first step in our MDP, like in an episode, and we might end up with in a totally new part of the state space where we don't have any data so far. And if we're not careful, like say we forget what we've seen, we might cycle and we might fail to improve. All right, but there's a couple different ways that we can address this issue. But the point is that this is an issue of distribution shift. This is an issue where I get some distribution, I update my policy, the distribution changes. So how can we address distribution shift? One way we can look at this is to try to somehow control what is the number of like effective state distributions that we can encounter. Like the idea here is, if I have a small number of possible distributions, as long as my algorithm doesn't forget what it's already seen, it's going to stop getting surprised by new distributions eventually, and we'll get meaningful generalization. So for example, like if we think back to this square CV method we saw for contextual bandits in the first part of the tutorial, here we were able to get a regret bound that scaled with the number of actions times the like supervised learning complexity for the function class we considered. And what was going on here was that the number of possible actions for this setting, which you can kind of think as controlling the number of effective distributions, this was small. So like as long as I explore enough, the number of times my algorithm gets surprised is just going to be proportional to the number of actions. And so this, strongly requires that the number of actions is small, but the nice thing was it wasn't placing any assumption on like what my hypothesis class looked like or what the context distribution looked like. But in general, for this style of reasoning to go through when we go beyond h equals 1, we need to place assumptions on the MDP we're looking at. Like if we think back to this exponentially large tree structured MDP from the first part of the talk where we have a reward at a single leaf, here there truly are like a to the h different state distributions, and that means we can get surprised many times. Okay, the other approach we can look at, which you might hope would place weaker assumptions on the MDP you're looking at, is to use some kind of hypothesis class that allows for extrapolation. And extrapolation here means, once I learn how the function behaves for some part of the state space, hopefully this tells me how it will behave for the rest. So like if you think back to this linear contextual bandit problem where we have rewards that are linear in some feature map, we had this LinUCV algorithm which gets proportional to the dimension of the feature map, which reflects that it's generalizing across contexts and actions. And the reason for this is like, because the rewards are linear, once we see, once we get a good estimate for the rewards along like a basis in D dimensions, we can extrapolate what happens on new directions that we may not have exactly seen before. And yes, the only issue with this is, potentially this is placing a strong assumption on what kinds of hypothesis classes will support. So we have these two approaches, bounding effective distributions, extrapolation. Both of these are going to make different assumptions on the MDP or the hypothesis class we're working with. And there's many different specific assumptions we can make to implement either approach that will lead to different algorithms and different sample complexity guarantees. And so the way we're going to structure the next portion of the talk is to explain how these approaches kind of come together to give the current like statistical landscape of RL as we understand it. So like so we're going to try to see like what are all the different assumptions we can make, and how do these relate to one another. Most of the terms, in this diagram, you won't be familiar with yet, but we're going to walk through them one by one and kind of get a sense for how they work. And just to explain, like what do these colors on this diagram mean? Green here is indicating like sample efficiency. Like this is some kind of assumption that leads to sample efficient learning guarantees. And red means not sample efficient, right? So like all of RL is not sample efficient because we've seen some bad examples already.
In this figure, like which of these boxes are driven by applications and domain knowledge from applications that will satisfy, and which of those are more like for theoretical convenience?
I mean, pretty much all of these are things that have come out of the theoretical community, but like once we go through some specific examples, I can, try to give a sense for how these relate to real applications. But I mean, I was actually going to touch on this at the very end. I mean, there's definitely room for, better incorporating kind of like real world considerations into the models we have. But, it's in that area of research that's developing very quickly right now. So yeah, so to start off, we've already seen tabular reinforcement learning in the first part, which is this little bubble. So our starting point is going to be to move out one step and look at reinforcement learning with linear function approximation in a setting called low rank MDP. So, the setup here is we're going to be working in a value-based setting, which means I'm going to take my hypothesis class to be a set of Q functions, which we're generating script Q. And we're looking at, perhaps the simplest value-based setting, which is where all my Q functions are linear in some fixed D-dimensional feature map, which we're calling phi. So for this approach to make sense, it seems natural that we should have our hypothesis class somehow be compatible with the underlying MDP. And a basic assumption we can make, which generalizes how we approached the contextual bandit problem, is realizability. This is just saying this hypothesis class script Q contains the optimal Q function Q star. For contextual bandits, we saw that realizability was sufficient for sample efficient learning. And this LinUCV method was able to get regret polynomial in the feature dimension. But the interesting thing is that it turns out for RL, once you go to multiple steps, this reasoning actually doesn't extend immediately. And there's a fairly recent line of work that shows if you only assume realizability, the optimal sample complexity for this problem is exponential in the feature dimension. So like sample efficient learning is not possible. And intuitively what's going on here is, okay, on one hand, you have this linear structure, which lets us extrapolate if we partially learn Q star. But on the other hand, once you go to multi-step RL, somehow this isn't helpful unless you have a mechanism to guide you toward Q star to begin with. So there's a stronger assumption we can place on the MDP, which will lead to sample efficient learning. And this is called the low rank MDP assumption. And so this property is going to say that our transition probabilities emit a low rank factorization with respect to this feature map phi that we're using to define our hypothesis class. So if we're looking at the probability that we transition to, say, x prime, given that we're in, say, x and take action A, we're saying this looks like the dot product of our feature map phi and another feature map mu of x prime. Now, so in this setting, we're assuming phi is known, but we're going to allow mu to be unknown. So this is still going to be a learning problem. But even though it's known, or even though it's unknown, this still like limits the complexity of our dynamics or our system. So if we're thinking of like P of x prime given XA as a big matrix, this is saying it has rank at most D. And I'll just mention, a good property to keep in mind here is this low rank MDP property. This implies that Q star is linear in phi, so it implies realizability, but it's actually stronger in the sense that it implies that all policies have linear Q functions. Any questions about this assumption? All right. So I'm going to describe an algorithm for this low rank MDP setting. This algorithm is called LSVI UCV. So LSVI stands for least squares value iteration. So, and this is going to be an algorithm which is still based on the idea of optimism and upper confidence bounds. So the idea here, and I'll walk through this step by step, is we're trying to compute an optimistic Q function, Q bar, that upper bounds the optimal Q function, Q star, everywhere. But the main difference between like this and the tabular RL approach we saw earlier is we're going to use least squares to incorporate a function approximation. And so I'll walk through this step by step. So, so first, as before, we're going to set our optimistic Q function Q bar to 0 at big step h plus 1. And then I'll describe sort of how we step backwards, assuming that we already have like Q bar h plus 1 computed. Okay. So the first step is we're going to solve this least squares problem with all the data we've collected so far. And this is saying, find me a parameter theta, which minimizes the squared error between the linear function induced by theta and the reward at the current step, plus my optimistic Q function Q bar at the next state. This is a little complicated, but it's motivated by the Bellman equation. So the idea is like, suppose I plugged Q star h plus 1 into this equation in the place of Q bar, then the Bellman equation tells me that Q star is actually what will minimize this squared error up to some like statistical deviations. Okay, so we're just simulating the Bellman equation. All right, and now once we have this parameter theta that solves least squares, we're just going to take Q bar h to be the linear function that theta induces, and then we're going to add a confidence bonus to ensure that we're optimistic. And I'll say more about how we choose this confidence bonus in a minute. But that's basically it. Once we have Q bar, we just pick the policy that optimizes it. All right. And what you can show is that this method has regret as well as sample complexity that's polynomial in the dimension and the horizon and has no dependence on the number of states. So you are in fact achieving exploration, generalization, and credit assignment. And this is also computationally efficient, which is nice. So let me explain how these bonuses work and kind of sketch the proof. So, just like the tabular setting, the crux of the analysis for this algorithm will be to show that it's optimistic. So Q bar upper bounds Q star everywhere. And to prove this, I need to say what the bonus we're adding to the Q functions is. And this is what we'll call like an elliptic bonus. So at episode T, we're going to let sigma HT be the sum of the outer products for all the feature vectors we've seen at step H up until this point. So this is something like a second moment matrix to the features. And we're going to set the bonus for XA to be like the norm of the features for XA, but under this sort of like reweighted Euclidean norm induced by the second moment matrix. So this is, we're just looking at the quadratic form of phi transpose sigma inverse phi, we're taking the square root. And so the fact that this bonus leads to optimism, this comes out of least squares, and it's related to this idea of extrapolation. And the point is, like, because we're working with linear hypotheses, sigma t captures how much effective data we have in different directions. So like if I see a lot of data in one direction, this quadratic form is going to be small in that direction, which reflects the fact that we're confident. Okay, and I won't go into detail about this, but once we have this optimistic Q function, just like in the tabular case, we'll be able to use the optimism property to show that our regret is dominated by the sum of these bonuses. And so all that remains at this point is to show that the bonuses are small, or they get small. And this is going to use a potential argument that kind of generalizes what we saw in the tabular setting. And this again will reflect our ability to extrapolate. So let's look at the sum of the bonuses for like step H within the episode. So the bonus for little episode T is this quadratic form of phi under the second moment matrix sigma T. And the idea is, well, let's suppose this bonus is big. This can really only happen if phi for the state T at time T extends in a direction that's not currently well covered by sigma T. But what's going to happen is, well, when we get to the next episode, we're going to add this feature vector to sigma T to get like, sigma T plus 1. So like the matrix for the next time step. And so the point is like, okay, our coverage might be bad at this step, but it is going to improve at the next step. And the good news is, because we're in a d-dimensional space, the effective number of times we're going to get surprised and shrink if we use this strategy will be proportional to d. And so indeed, you can show that this sum of bonuses is going to scale as like root dimension times t. Okay, so to summarize, this low rank MDP structure facilitates sample efficient learning with this mechanism of this extrapolation. And I'll briefly show now that we can kind of extend this idea of extrapolation slightly beyond linear models using a property that's called eluder dimension. So eluder dimension, this is a combinatorial parameter introduced by Russo and Van Roy, and it kind of gives a handle on how much the function class you're working with can extrapolate. I'll briefly define this. So eluder dimension is saying, let's say I have a function class script f. What is the longest sequence of points, z1 through zn, such that for each point zt in this sequence, there exists a pair of functions in this class that disagree on zt by epsilon. But if we look at their like root mean squared error on all the points that precede, it's at most epsilon. So this is asking you, like, in a pretty literal sense, if I look at functions that are close in squared error, how many times can I get surprised by new points? And this is pretty natural if you work with algorithms based on least squares, like the LSVI method we just saw. So eluder dimension means I cannot get surprised many times at a given scale before I stop making mistakes. And so indeed, like what Russo and Van Roy showed is, like, for bandits, you can get regret proportional to eluder dimension. I'm being imprecise about the dependence on epsilon here, but it's mild. And so this is for bandits, and it's reflecting the fact that you're able to generalize across actions. There's no states. But there's more recent work that shows that algorithms in the vein of like the LSVI UCB method we just saw can get regret that's polynomial in the eluder dimension of the value function class once I do reinforcement learning. This does require additional assumptions because like these are kind of in the vein of like the low rank MDP assumption. So like low eluder dimension on its own is not enough. Well, what's up? Or was there a question?
Yeah, just to understand a little bit, what is the domain of all these functions? Because if, for example, we are continuous, I can assume that the eluder dimension is infinite.
Yeah, it can be infinite. It's not always small. So actually, let me give some examples.
Okay.
But just to be clear, like when we apply this to RL, we're applying this to like a class of Q functions. So the domain will be like states by actions. But yes, it's not hard to construct examples where this is infinite, indeed. So like, if we look at some examples, for linear models, you can show that this is bounded by the feature dimension. And this is also true for generalized linear models. For example, if you have a linear model and then you just apply some nonlinear link to it, like sigmoid. But you can actually show, like, even just for like a single ReLU neuron, the eluder dimension can be exponential in the feature dimension. And indeed, there are other examples where it's just infinite. So morally, you should think of eluder dimension as like a slight generalization of linearity. And I have to say, it kind of remains to be seen whether there are like natural RL settings where eluder dimension is actually necessary and not just sufficient to get low sample complexity. But this is just sort of a consequence of the fact that, extrapolation is something that you can't really do when you go beyond, like far beyond like linear models. Okay, and so, with that in mind, what we're going to look at now is the other approach to handling distribution shift I described, which is, how can we control the number of effective state distributions that we encounter? So the way we're going to do this is using a notion which is called Bellman rank. So to motivate Bellman rank, I'm going to come back to this low rank MDP setting briefly. And we're going to make the following observation, which is if we, so okay, and just to recap, this is again, we're assuming P factorizes into phi dot product mu. So what we can use the low rank MDP structure to show is if I have just like, say, some function f of x, and I have some policy pi, I can write the expected value of f of xh for any h under policy pi. So like when I'm selecting my actions with pi, I can write this as the dot product of a vector x that depends on pi, but not on the function f, and a vector w of f, which is going to depend on the function f I'm looking at, but not on the policy pi. So we get this factorization as like a function of the policy and a function of the, a vector that depends on the policy, a vector that depends on the function I'm looking at. So the idea behind Bellman rank is there are certain functions where it's really useful to have this factorization property. And these are what we'll call Bellman residuals. So formally, the Bellman residual is going to be a function that depends on a policy pi that I kind of roll in with, and a value function q that I'm considering. And this is just the difference between the q function at step h and the reward at step h plus the q function at step h plus 1. So that's this quantity I'm looking at, but we're taking the expectation of this under a process where we follow policy pi until time h, and then choose the action that the policy induced by q wants to take once we get to time h. So why is this an interesting quantity to care about? Again, this is motivated by the Bellman equation. So if we look at the Bellman residual for q star, the Bellman equation tells us this is 0, regardless of what policy we roll in with, like what policy we play up to time h. And so evaluating this residual will give us a way of ruling out bad q functions that don't satisfy the Bellman equation. So returning to the linear MDP, if you use the property I sort of sketched above, we'll be able to show that the Bellman residual factorizes into a dot product of, again, a vector that depends on pi but not q, and a vector that depends on q but not pi. So in other words, if we look at this Bellman residual as a big matrix indexed by policies and q functions, this is saying the rank of this matrix is at most d. And Bellman rank is just a generalization of this property. It's just asking, okay, interpret the residual as a big matrix. What is the rank of this thing? So let me explain exactly what this sort of assumption buys us statistically. Well, what you can show is like whenever you have a realizable class of q functions containing q star, you can learn a near optimal policy with sample complexity that's polynomial in the Bellman rank, in the number of actions and the horizon, and most importantly in like the statistical capacity of your class of q functions. And the first thing to focus on here is this statistical complexity comp of script q this is exactly what we want. This is like a standard generalization error from statistical learning, like think log cardinality of your function class or finite classes. I'll just make a couple more remarks. So one is the bound I stated here, this depends on the number of actions. There are other variants of this property that allow you to generalize across actions so as well, so you can actually remove the number of actions in your bound in this case. The other point I'll say is, like, unlike all the settings we've looked at so far, we actually don't have computationally efficient algorithms for low Bellman rank in general. And there are some very interesting open questions here. Okay, so I'm going to describe an algorithm that achieves the sample complexity guarantee. This is an algorithm which is called bilin UCB. And this is a variant of another algorithm called Olive, which was the sort of first algorithm for this setting. Bilin UCB, like most of the algorithms we've seen up to this point, is based on the notion of optimism. And the name is coming from the fact that when we assume low Bellman rank, our Bellman residuals have this bilinear structure, so bilin UCB. Okay. And so this algorithm is kind of based on what are called confidence sets. So at each episode T, or each iteration, we're going to have this confidence set, which we call script Q, superscript T. This is going to be a subset of all the Q functions in our hypothesis class. And the point will be that we'll gradually shrink this as we get rid of bad Q functions. So let's walk through the steps. The first step will be, we're going to find what we'll call an optimistic Q function, Q bar T. The way we're going to do this is a little different from the other approaches we've seen so far. We won't explicitly be working with bonuses. Instead, we're going to define a function which is called JQ of pi. And this is the expected value of Q1 under the initial state distribution, where we're selecting actions with pi. And you can think of this as like an estimate for the average reward of pi according to Q. And so what we're going to do is we're going to pick Q bar T to be the function in our confidence set that maximizes JQ of pi Q. So you can interpret this as saying, find the surviving Q function that thinks most highly of itself. It could be wrong though, so we need to make sure, we need to make sure we take care of that. But once we have Q bar T, as usual, we're going to take pi T to be the greedy policy for Q bar T. So just the policy that maximizes Q bar T. And then there's two more steps. So the first step, I won't go into detail about how we do this, but the idea is by running pi T for a small number of episodes, we'll be able to get an estimate for the Bellman residual under pi T that's close for all the Q functions in our Q function class. And then the way we're going to update our confidence set is by keeping only the Q functions where the sum of squared residuals that we've estimated so far is small. Oh, sorry about this. There's a typo here. So the Bellman script E in this definition should have a square on it. Okay. So we're just keeping the Q functions where the sum of Bellman residual squared is small. The motivation being, we know that Q star has 0 Bellman residual up to some small statistical error. Okay, but to summarize, each iteration of this method is going to have sample complexity that's polynomial in all the parameters we care about. So we just need to control how many iterations this takes before we get a good optimal, before we have an optimal policy, or before our regret starts shrinking. Okay, and I'll quickly walk through the analysis here. So just for reference, at the top here, again, I'm just displaying the definition of the Bellman residual, and we'll recall that this factorizes into this X of pi component and this W of Q component in D dimensions. That's by assumption. So the first step in this analysis is to show that Q star is never eliminated. So Q star always stays in our confidence set. And this is pretty natural. Again, this just follows from the Bellman equation, which says that Q star has 0 Bellman residual for any policy. Okay. And as a result of this property, we'll be able to show that Q bar is optimistic, although in a slightly different sense than what we've seen so far. So it's kind of optimistic on average. What I mean by this is that this quantity J Q bar T of pi T, which we said is what Q bar thinks its average reward is, this upper bounds the optimal reward. Okay, Now, the next step is using kind of like a telescoping argument. You can actually show that for any Q function, the difference between what it thinks its average reward is and the actual average reward of the induced policy, this is bounded by the sum of Bellman residuals, which if we use the Bellman rank property, is the sum of dot products of factors that depend on pi and factors that depend on Q. And in particular, if you combine this with optimism, you can show that like the suboptimality of the policies selected by this algorithm is bounded by the residuals by these Bellman rank kind of factors, where we're taking the dot product of this factor that depends on the policy we play and this factor that depends on Q bar T. Okay, and finally, the idea is, because we defined this confidence set in terms of the Bellman residuals from past rounds, which also have this bilinear structure, we're going to be able to bound this error in the residual as, sort of like this weighted Euclidean norm, very similar to what we were looking at for the low rank MDP setting. So this is a norm that's defined based on all of the X components for our Bellman rank factorization that we've seen so far. And again, this is going to quantify what are the effective directions in which we've seen a lot of data so far, but in a kind of more problem dependent sense than in the low rank MDP setting. What I mean by that is we only care about directions we've seen data kind of projected onto these Bellman residuals. So the point though is, using the same sort of potential style argument I sketched for the low rank MDPs, you can show that these norms go to 0 at a rate that's proportional to the Bellman rank. And that's kind of it. Okay, are there any questions on this before I move on and look at some examples? All right. Yeah, so let's make this a little more concrete. So we'll just walk through some settings that have low Bellman rank. This is maybe a little related to Vasilis's question earlier. The first couple of these we can check out are just, we can verify that for the tabular setting, like finite states and actions, you can always bound the Bellman rank by the number of states, which is a good sanity check. And likewise, as we saw for low rank MDPs, the Bellman rank is always linear in the feature dimension. Another example, which will be familiar if you're coming from like the control theory side, is if you look at like the linear quadratic regulator, this is sort of the canonical optimal linear control problem where we have continuous states and actions. And you can show that the Bellman rank for this setup scales just with like the state dimension and the action dimension. All right. There's many other examples you can consider. One that I want to focus on is what's called the block MDP. So the block MDP is a model that's trying to capture how can we do sample efficient learning when we have rich observations. So like the setup is, I have like a large high dimensional state space, but we assume these states can be uniquely mapped down into a small unobserved latent state space that is responsible for determining the dynamics. Like the motivation being, if we're trying to play a game like Atari, our states might be images of the game, which we can represent as raw pixels. And these are very high dimensional. But the underlying game state, like if we think of, maybe the coordinates of our paddle, if we're playing Pong, this is pretty simple and low dimensional by comparison. And so we can model this by, assuming that the latent state space is finite. And that means that if we could observe the latent state space directly, we could just use like tabular reinforcement learning to solve the problem. But the catch is we don't know the latent states, and we also don't know what the mapping from observations to latent states is. So we need to use, modeling and function approximation to learn this. And so what you can show for this setting is the Bellman rank here actually only depends on the number of latent states. And this means you can get sample complexity that depends only on the number of latent states and actions, not on the number of observed states. So the only catch is you need your Q function class to be realizable, so like to contain Q star. And this means like your Q functions need to be flexible enough to represent this mapping from observations to latent states. So that's the kind of the way the modeling will come in here. And I'll briefly just mention the way you prove that the Bellman rank is bounded by S here is just by writing the Bellman residual as a sum of probabilities for visiting each of the latent states times Bellman residual conditioned on the latent state. And because there's only like, cardinality of script S latent states, you can write this as a dot product in like S dimensions. Okay. I'll touch on one more example, and that's just if we come back to this low rank MDP setting, we use the low rank MDP structure here to show that the Bellman rank was at most D, because we can write it as, this product of these two D-dimensional factors. But the point I want to highlight is that like when we originally looked at the low rank MDP setting, we were assuming that this feature map phi was known. But this argument that we have low Bellman rank here, this actually works even if phi is unknown. And so this implies that you can do sample efficient RL in low rank MDPs, even if you don't know the features. And the only catch is just like in the block MDP setting, you'll need a bigger Q function class script Q to represent the unknown features if you want to satisfy realizability. I'll just do a little more discussion of the low rank MDPs. So first of all, the methods we've looked at for Bellman rank so far, these have been value-based. Like our hypothesis class was a set of Q functions. There are some MDPs where modeling the Q functions requires high sample complexity, but you can get low sample complexity if you model the transition probabilities directly. So you take a model-based approach. And there's a variant of Bellman rank called witness rank that handles some of these cases. I'll also just mention there are other kind of more general assumptions you can make on how the Bellman residuals factorize. These can also lead to tighter guarantees in certain settings. And so if you take these into account, the full landscape will look something like this. So we have like witness rank, this model-based property is allowing us to extend beyond Bellman rank. But the natural question you might be wondering at this point is, like, what is the true shape of this landscape? Like, I've given all these conditions that I said are sufficient to derive sample efficient reinforcement learning algorithms, but like, what about necessary conditions? So where does this green tractable portion of the landscape end? So the last thing I'm going to go over is a very recent result. And this is like, we have a new complexity measure that does exactly this. So it's called the decision estimation coefficient, and it gives necessary conditions for sample efficient RL, as well as actually sufficient conditions. So the decision estimation coefficient, this is a complexity measure that's going to be defined in a model-based setting where we're modeling transition probabilities, or like our hypothesis class is just a set of MDPs. So each MDP in this class has its own probabilities and rewards associated with it. And just like we've been doing for the other RL settings, we'll make a realizability assumption and assume that the true MDP M star is contained in this class. Now I just need to give a little bit more notation here. So for a given MDP in the class, we are going to let M of pi denote the distribution over trajectories that we get if we run policy pi in the MDP. We're going to let Jm of pi denote the expected reward for pi if we run it in the MDP M. And we're going to let pi star M denote the optimal policy for the MDP M. So, okay, so with these out of the way, I can define this complexity measure. I'll walk through this step by step because there's a lot going on. But this is a complexity measure which we're denoting like DEC. And this has 3 parameters. So it depends on this model class script M. It depends on what we'll call a reference MDP, which we're denoting M bar. And then it depends on a scale parameter that we'll call gamma. And so let me walk through this full expression. So this decision estimation coefficient, this DEC, this is the value of a min-max game. So that's actually in line with the theme of this program, where we're trying to find a distribution over policies for the learner. So this is represented by the min player, such that for a worst case MDP in our class, which is represented by the max player, if we look at the expected value of a policy sampled from the learner's distribution, we are looking at the difference between the suboptimality, or like the regret of their decision, which I'm highlighting here, And we want this to be controlled by the estimation error relative to the reference model M bar. So here, when I say estimation error, we're looking at like Hellinger distance, which is a distance metric between, it's a distance between distributions. And we're looking at the difference between the distribution over data induced by the policy we're selecting between this worst case model M and the reference model M bar. I'll just mention very briefly, if you're more familiar with KL divergence, you can substitute KL in for Hellinger here. The difference is not very important for this setting. Okay, so I just said a lot about this expression. Let me just summarize what this actually means conceptually. So conceptually, the way you should think about this is M bar is a guess for like the true model, the true MDP. And this decision estimation coefficient, this DEC, this is asking, like in a very literal sense, what is the strategy for the learner that achieves the best trade-off between the regret of the policy they select and the information that they acquire by selecting this policy? And they're doing this in the face of an unknown environment. And then the scale parameter gamma here is just controlling this trade-off between like regret and information. Okay, and I'll just finish off this definition by saying that what we really care about is like the max of the value of this thing over reference models M bar in our class. Okay, that is the definition. Are there any questions about the definition here? Oh, looks like there's a question in chat. Give me 1 second. Costas is asking, where is P in the game? P is right outside. If you look at this expectation right outside the brackets here, we're sampling the policy from P. Wait, was there another question? Okay, cool, great. Okay, so the reason why we care about this parameter is this gives a necessary condition for sample efficient RL. So we can show the following lower bound in terms of the DEC. So for any class of models script M, there is some model in this class or some MDP in this class where your regret for any algorithm is going to scale as the min of two quantities. So one is this decision estimation coefficient at scale gamma times T, and the other is gamma itself. Okay, and then we're taking the worst case value of gamma for this expression. So, intuitively this says if the DEC is large, your regret has to be large, but it's easiest to just walk through a couple examples that give a sense for how this lower bound behaves. So first of all, for the multi-armed bandit, you can show that the DEC at scale gamma is proportional to the number of actions divided by gamma. So if you plug this into the lower bound, your regret is lower bounded by, the min of these two terms, AT over gamma and gamma. And the optimal value of gamma here just balances these and it gives you root AT, which is the min-max rate for this setting. So you're recovering like the optimal lower bound. Another basic example is you can show for the Bellman rank setting that the DEC, is lower bounded by the dimension of your factorization, again, divided by gamma. So if you do the same calculation here, you get the regret is lower bounded by root dimension times T, okay? And both of these examples are like statistically tractable settings, but the cool thing is that this can recover impossibility results or intractability results. So if we look at the setting I mentioned before, where we assume Q star is linear in a feature map in D dimensions, but nothing else, here you can show that the DEC is exponential in the feature dimension. So if you plug that into your lower bound, yeah, you see that the regret for any algorithm has to be exponential. You're recovering the fact that the setting is not tractable. The last thing I'll say about this complexity measure is I stated this kind of coming at it from the perspective of lower bounds, but this is actually very easy to operationalize and kind of make algorithmic. So we have an algorithm based on this complexity measure, which is called estimation to decisions. And you could think of this as a generalization of this like square CB method that we saw for contextual bandits. And I'll just quickly walk through this. So the idea is at each episode, we're going to get some estimate for the MDP using our some supervised estimation algorithm, like this could be density estimation or something else. And it's going to give me this estimator just based on all the data I've collected up to this point. Then once you have this estimate, we're going to find the distribution over policies that like solves the min-max problem that defines the DEC when you have m hat t plugged in as your reference distribution. So this is just, before when I defined the DEC, I defined it as a min-max. Now we're just looking at the argmin for the exact same min-max. And then once we get this distribution over policies, we're just going to sample the policy to play from this distribution, and then we'll update our supervised estimation algorithm with the data we see. And so what you can show is that this strategy actually achieves a regret bound that matches the lower bound I showed on the previous slide, up to the addition of an extra term that kind of corresponds to how well is your supervised estimation algorithm doing. So we have this term est sub h here. This is just the sum of Hellinger distances between all the estimates that your supervised estimation algorithm has produced and the true model or true MDP M star. And this estimation error, this is a classical quantity. So, this is something where you can show, like if I look at, say, finite classes, this is like log cardinality of the function class. If you look at parametric models, this is going to scale with the dimension. And so the point is, this is achieving the same regret bound as in the previous slide, but the gamma term is scaled by this estimation error. So conceptually, this is saying, as long as this DEC is small, and as long as you can estimate well, you can achieve low regret. And so in particular, what this means is for classes of MDPs where you have like bounded supervised estimation complexity, the DEC completely characterizes when sample efficient learning is possible. And I'll just mention, to tie this back again, the square CB method we saw for contextual bandits, like both the algorithm and the analysis are actually special cases of this result.
Dylan, may I ask
one
short question, just to understand something.
Yeah.
The min-max problem is easily solvable?
That completely depends on the structure of the problem. Yeah.
So I mean, in the general case, could be non-convex, non-concave, right? Or not?
Oh, good question. No, so it's linear with respect to the learner's strategy.
Right. But
So,
as far as the how about the space of the Markov?
Yeah. So exactly. So that's where you kind of need to use additional problem structure. So like there's tons of special cases where we know how to solve this. So like essentially we know how to solve this efficiently for most of the settings I've covered in the talk up to this point, but there are many open questions here, and I can say more about that offline. Yeah. So yeah.
Another question. So given that this has some information theoretic sort of like spin, is there any relation with the Russo-Van Roy type of approach for multi-arm bandits?
Oh, are you talking about the information ratio?
Yeah.
Yeah, that's a great question. So yeah, information ratio is like a kind of, it's another, you could kind of think of it as a complexity measure for bandits. Yeah, so you can actually show that this DEC is always upper bounded by the information ratio. In general, though, there are models where like the DEC is small and the information ratio can be arbitrarily large. But there are actually some deeper connections. I can say more about that offline as well. Cool. Okay, we're coming towards the end. I'll just briefly summarize these approaches we saw to the RL problem. And these are ways of attacking distribution shift. So on one hand, we saw that we can attack the problem using the idea of extrapolation, using, say like linear models in low rank MDPs and using eluder dimension. And on the other hand, we saw that you can try to control the effective number of distributions using notions like Bellman rank. And then finally, this decision estimation coefficient, this acts as a converse and it provides necessary rather than just sufficient conditions for sample efficient learning in RL. And that's going to bring me actually to the end of the tutorial. So just to come back to the broader message, we saw these three challenges. We saw exploration, we saw generalization, we saw credit assignment. We saw, that we have classical solutions to these individual challenges, as well as solutions when we pair them. And really the frontier of theoretical RL is trying to put them all together, like exploring with a long horizon while we generalize across states. This is a problem where we have to make modeling assumptions to get sample efficient learning guarantees. We saw a bunch of different ways of doing this, but there are a ton of open questions, and this is really like an active line of research. I think on one hand, a lot of research required to come up with new models that kind of better capture considerations of real world RL problems, beyond like many of the idealized settings we've seen so far. And I think, with some of these new tools we've gotten over the last couple of years, we're in a much better place to do this than maybe we were in the past. And I'll also say, while our understanding on the statistical side is kind of starting to take shape, computation and like computational efficiency, is a place where there's still a lot to be done, even just for the settings I discussed today. Okay, and lastly, I'll just give a little bit more of a teaser for like Chi's tutorial later in the afternoon, right? So the point of this is going to be, how does everything I talked about today change once we have an MDP that kind of has like multiple agents operating in it, either like in cooperation or adversarially? And this raises some cool issues, right? So, we can think about, I talked a lot about function approximation and modeling today. How does this change once, I have, say, like an opponent? Like, what do I need to be able to model about what my opponent is doing? Or, we looked at, this optimization perspective on RL in the first part of the tutorial. Once we go to multi-agent RL, that becomes something maybe close to a min-max optimization perspective, right? So this is also very much along the lines of the theme of this workshop and program. So those are just a couple questions. There's many more, but I think it should be a lot of fun, and I'm looking forward to it. So yeah, with that, I can stop and take questions.
Thank you very much, Dylan.
Yep.
This was an excellent tutorial. Thanks.
Thanks.
Any questions?
Hey, Dylan. I want to ask about, so I think in major part of this talk, you're talking about like how people make assumption on the complexity of this reinforcement. Making some like complexity assumption on this entire reinforcement learning procedure. I want to say like how robust is it for practice? And I think in general, in practice, people are just using some like simple, like for example, epsilon gradient or something.
Sure.
What's the major gap between this theory and practice?
Yeah, so I guess the thing is, okay, there's a couple questions there, right? The thing is like these epsilon greedy approaches, right? Like, so a lot of what I talked about today was really trying to understand how to do like exploration, like how to systematically explore. Because like in the worst case, things like epsilon greedy, these don't systematically explore, and they can have, sample complexity, like let's say like exponential in the horizon. Now, if you're trying to solve some, real world problem, it depends on how you're trying to solve it. So if you have like a simulator or something where you can just get tons and tons and tons and tons of data, like billions of rounds of interaction, you can potentially overcome this. And that's especially true, or so I should say overcome this without systematically exploring. And that's especially true if you have kind of like a nice MDP that, maybe is not worst case, right? But I think like understanding these issues of like, how do we combine exploration? This is going to be important as we move into problems that have like longer horizon, or where we maybe have like less data available, like where sample efficiency becomes like a real concern. So that's kind of like the motivation. Okay. Oh yeah, and you said how robust are these things? That's a good question. So like most of the methods I talked about today, are going to make some assumption like realizability, and pretty much all of them are going to degrade in like reasonable fashion if this like realizability only holds like, let's say like epsilon approximately. But the real question is like, well, does this realizability hold epsilon approximately to begin with? And I think if we go to settings like where you really have continuous state and action spaces, it's not clear that any of the models we have yet are like a really great fit for this, or give something that you could actually try running yet. So that's an area where I think there's a lot more to explore. Oh, it looks like there's a question from Kostas in the chat. Oh yeah, Kostas is asking, there's some contention between the structure and the MDP, like the realizability assumption, and which necessitates a rich class of models. Any thoughts on non-realizable settings? That's an interesting question, right? So you can think about agnostic versions of RL. You can think about like settings where I just say, maybe I just start off with some small class of policies and I want to compete with the best in class. Unfortunately, you can show that like being agnostic is not really possible in a sample efficient manner without further assumptions. And so for example, like, you can come up with settings where I have a very small hypothesis class, like maybe only 2 hypotheses that I care about, but I still need like exponential sample complexity to figure out which one is which. So like just the fact that I'm trying to be agnostic doesn't help me much. And the interesting thing is like, so basically you still need to make modeling assumptions, but like, I do think that this, like being like semi-agnostic is interesting to explore. There are some very concrete questions there that I've been thinking about. And I think we're actually in a pretty good position to attack this problem with some of this machinery we've developed for like the DEC that I was just talking about.
Great, so let's end here. There's going to be a 2-hour break. Not 2-hour break, we're going to be back at 2 for Jean's tutorial on multi-agent RL. And thank you again, Dylan, for this wonderful tutorial.
Thanks a lot. And thanks for coming, everyone. So hopefully we'll get to hang out more in the near future.